Welcome everyone to our May seminar. The topic of today's seminar is opportunities for geothermal and thermochemical energy. My name is Dr. Andy Smallbone. I'm an associate professor at Durham and I'm the director of the Network Plus. This event is organised through that same Network Plus, which is the network for the decarbonisation of heating and cooling, and is a part of its monthly series looking at different challenges of decarbonising heating and cooling. This month, we're delighted to welcome speakers from Newcastle and Nottingham universities who are leading research around geothermal opportunities and thermochemical energy storage. So we're welcome and we are very grateful to both presenters for presenting and providing their time today. We're going to move on now to the second presenter, who's Yong Zhang. Yong will be talking about modeling analysis of a thermochemical energy storage reactor embedded with novel internal heat exchanger. Yong is a PhD researcher in the Buildings, Energy and Environmental Research Group at Nottingham University, and he's working with the team of Professor Su on thermochemical energy research. So you take it away, Yong, in your own time.
Okay. Thank you, everyone. Thank you for coming to the presentation. Today, I will discuss the topic of thermochemical energy storage system combined with the heat recovery and internal heat exchange. I will keep it concise, take only 20 minutes of your time. If you have any question, I will be happy to answer that in the end. To provide the structure in my presentation, I have divided into three parts: introduction, review, system description, mathematical model and validation, results, and discussion and conclusion. Let's start with the introduction and background. With the growth of the population of the development, industry, the world's total energy consumption have continued growth. According to the data from the International Energy Agency, the world total energy consumption was 418 BTU in the 2019, which show an increase of 115 over 1973. Due to the impact of the COVID-19, the energy consumption of residential sector have improvement. According to the report from the UK government, in the UK, the residential sector become the second largest energy consuming sector, and account for the 31 of the total energy consumption. Most of the residential sector energy consumption is supplied by natural gas and electricity. Renewable energy only provides a 5% of the energy used in the residential sector. We can learn from the pie chart. The heating application are main energy consumption terminal in the residential sector. They account for 18.5% of the total energy consumption of residential sector. Use more renewable energy in the heating application is the potential solution to reduce the carbon dioxide emission and fossil energy consumption. Solar energy is considered one of the most potential power in the future, especially in the residential sector. However, due to the intermittent of the solar energy, it can't meet residential sectors with heating demand, closing the gap between the residential sector energy demand and solar energy supply remain a challenge. Nowadays, thermal energy storage technology is widely considered to be a potential for this problem. Thermal energy storage can be divided into three common methods, like in this table. Sensible energy storage, limited thermal energy storage, and thermochemical energy storage. Thermochemical energy storage using reversible chemical reaction to store the thermal energy, and it have a higher energy store density compared to other two methods. The thermochemical energy storage system has a small value and ignorable thermal loss during the long-term energy storage, which make it potential for the seasonal energy storage. The operation process of the thermochemical energy storage system is divided to three steps. First, the components A and B dissociate into separate A and B in the high temperature environment. The process is called the charging. After that, the A and B keep separate storage. This is called the storage process. Finally, when the A and B come into contact again, the component AB is formed with the heat release. The process known as the discharging. After the discharging process, the thermochemical reaction enters in the next cycle. Due to the energy is stored as the chemical potential during the storage process, the energy loss is ignorable in the process. Current, the thermochemical energy storage system research focus on use the air as thermal energy medium, but the water-based system have been overlooked. However, in the UK, 1905 of household rely on the central heating system that circulates water for the heating. Air-based, the thermochemical energy system operating independently and can easy to change for the central heat system. So this is a challenge. This study presents new thermochemical energy storage system that there have the internal exchanger and the heat recovery device. This system uses the water as the heat transfer medium. They can make the heat direct transfer to the central heat system. The system proposed in the study shown in the figure 6 includes the various components: a reactor with the internal heat exchanger and air-to-air the heat exchanger and pop fan and humidifier. During the discharging process, the core air from the surrounding enters the heat exchanger and preheating by the hot air from the reactor. Then the heated air is humidity. Use a humidifier. The air into the reactor when the thermochemical material absorbs the water and releases the heat. Some of the heat is transferred to water through the internal heat exchanger, which is supplied building central heat system. The remaining heat is transferred to the airflow before leaving the reactor. Finally, the warm airflow passes through the heat exchanger once again before into the environment. This is the 3D reaction model. This is the reaction bed and internal heat exchanger. The reaction bed and heat exchanger is positioned in the middle of the center, in the center of the reactor, with the air pass through from bottom to top during operating. In the reaction bed, there have 10 internal heat exchanger channel runs through the reaction bed with water as the heat exchanger medium. In other space, is filled with the thermochemical material. This our mathematical model. Our mathematical model was validated against the experiment data. There have good agreement. The model accurately predicts the performance of the proposal new system with the RMSD value of the 2% for the reactor outlet airflow temperature and only 0.5% for the internal heat exchanger outlet water temperature. This figure showcases the change in the conversion degree and the rate of the salt hydrate in the reaction beds, and the temperature of reactor outlet airflow and the internal heat exchanger outlet water temperature. The conversion rate of the solid hydrate initially increased quickly, peak at the second meaning. At then, the gradually decrease as saturation is reached. Similarly, the temperature of the airflow and the water flow follow the same patterns, reach the max value at the 8 minutes. After that, the declining until the discharging process ends. The overall thermal efficiency of the new system is impressive, calculated at 18.3. The include of the heat recovery device in the new system have significantly improved compared with the original system, which only have the 12% thermal efficiency. Next, we show the impact of the operating parameter on the thermal efficiency. This figure shall highlight the influence of the reaction system airflow into inlet temperature and internal water flow inlet temperature. The air reactor inlet temperature enhances the thermal efficiency, while the air internal heat exchanger inlet water temperature decreases it. The system reaches its peak thermal efficiency of 1992 in the region when the inlet temperature in the 24 and the water temperature in the 25 degrees centigrade. Furthermore, the velocity of the airflow in the reaction bed and water flow in the internal heat exchanger play a significant role. This figure shows the impact on the thermal efficiency. Increase the water flow in the velocity in internal heat exchanger contribute to improve the thermal efficiency, while the airflow velocity has is decreased effects. In the region, the system reach the thermal efficiency around the 90. To conclude, when our study provides a new thermochemical energy storage system combined with the heat recovery and internal heat exchanger, by harnessing the thermochemical energy storage system, we can efficiently store and use the thermal energy, providing the way for increased increased renewable energy in the heating application. The end of the heat exchanger significantly enhances our thermal efficiency of the system by the change the operating parameters such as the reactor inlet temperature and internal heat exchanger inlet water temperature. We can achieve a high thermal efficiency level. Thank you for attention.
Thank you, Yong.